Okay, let's unpack this. We have a massive stack of research sitting here today covering, decades of computer science history. But before we even look at the title of this paper, we need to talk about a lie.
Oh, a massive foundational lie.
Right. I'm talking about the greatest fiction in software engineering, like a widespread, industry-spanning, universally accepted lie that we all just politely agreed to ignore at parties.
Yeah, the one every developer is guilty of.
Exactly.
Yeah.
We write a piece of code, right? Maybe it's I don't know, a new rendering engine or a database query optimizer. And we sit there looking at our IDE and we tell ourselves, oh, I will definitely run this through a rigorous profiling phase.
Right. I'm going to be so responsible.
Yeah. I'm going to instrument this binary, deploy it to a staging environment, gather incredibly detailed telemetry on how the users actually use it, and then I'll feed all that rich empirical data back into my compiler so it can perfectly optimize all the hot paths.
Here's the thing, though. Literally nobody actually does that.
Nobody. It's a total myth. We build the thing, we run a couple of automated unit tests that execute the exact same, completely predictable, totally synthetic paths every single time.
The happy paths.
The happy paths, exactly. We look at the green check marks on the screen, we declare the software optimized, and we ship it to production. We lie on the JIRA ticket, and we move on with our lives.
And then it hits the real world, and, well, the real world is absolute chaos.
Oh, complete entropy.
Right, because you assume your users are going to gracefully navigate your application step by step. Instead, they click buttons in the wrong order. They feed your data parser a million rows of malformed CSV data when you expected, like, 10 pristine rows.
Or they unplug their mouse halfway through a transaction.
Exactly. They run your application on bizarre, underpowered hardware that you didn't even know existed. So that static profile data that a developer meticulously gathers in a controlled lab environment, it's essentially a work of fiction compared to the end user's actual incredibly weird behavior.
Which, and this is the perfect pivot, brings us to the year 2002. Today, our deep dive is looking at Chris Lattner's 2002 master's thesis. Our mission today is to figure out how this single academic document completely rewired the foundation of Apple, Rust, and basically modern software architecture.
Just by assuming developers are impatient and users are chaotic.
Exactly. The paper is titled LLVM, an infrastructure for multi-stage optimization. And I know, this thesis has more Greek letters than a fraternity.
It is incredibly dense.
The title alone sounds like it's going to put you to sleep. But hear me out, because the implications of this document are literally still echoing through the silicon of the device you are listening to this on right now.
What's fascinating here is that to truly appreciate the sheer magic of LLVM, you really need to put yourself in the shoes of a software engineer back in the early 2000s. Hardware designers back then were losing their absolute mind.
Oh yeah, Moore's Law was in overdrive.
Completely. We were seeing the Pentium 4 era. Intel and AMD are slapping longer and longer instruction pipelines onto their chips. They're stacking up complex cache hierarchies, L1, L2, L3 caches.
Just throwing silicon at the problem.
Exactly. They're throwing parallel execution resources, superscalar architectures, out-of-order execution, just everything they can think of at these CPUs at breakneck speed. Hardware is running a marathon.
And compilers are suffocating. They're stuck in the mud wearing concrete shoes.
Yeah, they were completely trapped in this rigid, archaic compile, link, execute model. It's basically a relic from the 1970s.
So you, the developer, you had to make a brutal zero-sum choice. Either you choose terrible runtime performance for your user, or you choose unbearable, soul-crushing compilation times for yourself.
There was no middle ground.
None. And that's where Lattner steps in. His entire premise, the absolute bedrock of what became LLVM, is built on a very simple, very human observation. Human patience is strictly limited.
It really is the ultimate bottleneck in computer science. I mean, you can have the fastest algorithms in the world, but if a developer has to wait 45 minutes to see if their one-line code change actually fixed a bug...
Your ecosystem is dead. Nobody's going to iterate on that.
Right. They'll just go check their email and lose their flow state.
So we are going to tear apart how LLVM solved this bottleneck. We're going to see how it completely re-architected the way we translate human-readable code into machine instructions, and how it essentially created a paradigm where software can observe itself, rewrite itself, and adapt to that chaotic, real-world user behavior while you're not even looking.
But, and this is crucial, to understand the cure, we have to deeply understand the disease.
Right, let's diagnose this.
When you say compile, link, execute, it sounds so clean, so modular. But under the hood, the early 2000s compiler landscape was just a bloody battlefield of trade-offs.
Let's paint that picture for the listener. Imagine you're a C++ developer in 2002. You want your massive enterprise program to run fast. And I don't just mean fast in isolated little pockets. I mean across the entire program. You want what's called interprocedural optimization.
Right, the absolute holy grail.
You want the compiler to look at a function in a file you wrote, say filea.cpp, and a totally different function in a file your coworker wrote -fileb.cpp. You want the compiler to figure out how they interact so it can optimize them together.
Like maybe it realizes it can inline your coworker's function directly into yours, saving a massive amount of call overhead.
Exactly. Which is incredibly hard to do because traditional compilers have tunnel vision. They process one file at a time. The compiler looks at file A, translates it, completely forgets it, and moves to file B. It has zero whole program context.
Not at all.
So, the industry, recognizing this tunnel vision was killing performance on these fancy new Pentium chips, tried a few approaches. Approach number one was link-time interprocedural optimization.
Waiting until the very end.
Right. The idea was, let's wait until the linker stitches all the files together to do the heavy optimization. And within this approach, there were two totally opposite philosophies. The first was the machine code route. This was used by systems like Dynamo.
Dynamo is a great example. In the machine code route, you let the compiler front end translate everything down to the absolute lowest level right away. It takes your beautiful high-level C++ code and instantly shreds it into native machine code.
Just raw zeros and ones?
Basically, yeah. Just raw bytes, registers, and memory addresses. Then, at the very end, at link time, the optimizer tries to massage that raw machine code.
Wait, so you're telling me this actually works? You don't have to rewrite your front-end compiler, you just tack a really smart linker onto the end.
Well, it works, technically. But you run into a massive wall. Machine code is spectacularly dumb.
How so?
It has aggressively stripped away all the context of your original program. When the machine code optimizer looks at those bytes, it doesn't know what an array is. It doesn't know what a customer profile struct is.
Oh, because it's just looking at memory offsets.
Exactly.
Yeah.
It doesn't know if a loop is iterating over a linked list or just counting to 10. It just sees raw bytes moving into registers and out to memory addresses.
Okay, so you're saying the optimizer is trying to read a book where all the punctuation, the paragraph breaks, and the chapter titles have been totally deleted.
That's a great way to put it. You could do some basic microscopic optimizations, like you can shuffle a couple of registers around to save a clock cycle here or there. You can maybe string together a trace of a few instructions.
But you can't see the big picture.
You cannot do aggressive whole program macroscopic analysis. You can't safely rearrange massive blocks of memory because you don't know what that memory represents anymore. The context is just completely gone.
Okay, so if the machine code route fails because it strips away too much information, the natural engineering response is to violently overcorrect and go the exact opposite way. Enter the AST route, the abstract syntax tree approach. This is what massive, heavy-duty systems like SUI for SGI Open64 did.
Ah, yes. The high-level bureaucracy approach. I love this one.
Let's explain what an AST is for a second, just so everyone's on the same page. When a compiler reads your code, it doesn't just read it left to right like a book. It builds a literal tree data structure in memory.
Right, a mathematical tree.
Yeah. If you write A equals B plus C, the root of the tree is the equal sign. The left branch is A. The right branch is the plus sign, which itself has two branches, B and C. It's a mathematically pure representation of your program's grammar.
And it's incredibly rich. It contains every single piece of high-level information you could ever possibly want. Types, structures, variable names, scope boundaries, it's all right there.
Right. So in this AST approach, the compiler takes your source code, builds this massive complex tree structure, and instead of compiling it down into machine code, it literally takes that gigantic tree and saves it to the hard drive. It serializes it.
Just dumps it on the disk.
Yeah, and it does this for every single file in your project. Then, at link time, the linker reads in all of these massive gigabyte-sized trees from the disk, stitches them together into one gargantuan program-wide megatree, and tries to optimize and generate machine code from that.
And here's the plot twist. It takes the rest of your natural life to finish.
Wait, really? Is it that bad?
It is so bad. Think about it. In this model, almost all the actual compiling work, the heavy lifting of translating logic into hardware instructions, is postponed to the very, very end of the process.
Oh, man.
Every single bit of it. Which means you, the developer, are sitting there trying to debug a tiny UI glitch. You decide to change one integer in one file from a 0 to a 1, just a tiny microscopic tweak.
Right.
You hit build. And because all the real work happens at link time, dealing with the entire program's massive bloated AST, the linker has to basically process the entire world again. You literally have time to go make a sandwich, eat it, stare out the window, have a small existential crisis about your career choices, and maybe watch an episode of television before the build finishes.
The human patience bottleneck strikes again.
Yeah.
You cannot have an agile, iterative software development cycle if your build takes an hour for a one-line change.
SGI Open 64 basically demanded you schedule your compilations around your lunch breaks. It was absurd.
Okay, so ASTs are too slow and bloated to build, and machine code is too dumb to optimize. What was approach 2?
Approach 2 was high-level language virtual machines. If you were working in the late 90s or early 2000s, this was the shiny new toy. Think early Java, Smalltalk, or Microsoft's C# Common Language Runtime.
The JVM approach, the whole write once, run anywhere promise.
Exactly. You compile your source code into a high-level machine-independent bytecode. You don't compile it for an Intel chip or an AMD chip. You compile it for a fake virtual machine.
Right, and then at runtime, when the user double-clicks the app, a just-in-time compiler, a JIT, reads that bytecode and compiles it into native machine code on the fly. It's wonderfully portable.
It's portable, and it's secure because the VM can sandbox everything. But I'm guessing Lattner saw a fatal flaw here, too.
Oh, absolutely. The fatal flaw is just a matter of physics and time. The JIT compiler is a piece of software running on the user's machine.
Right.
It has to work incredibly fast because the user is literally sitting there staring at a loading screen, waiting for the program to launch or waiting for a new level in a game to load.
That's a zero-sum game, though.
What do you mean?
If the JIT is running complex optimization algorithms, it's eating CPU cycles. Those are cycles that the user's actual application, the video game, the database, the web server needs to be using.
Oh, wow. I never thought about it like that.
Precisely. The JIT is stealing valuable cycles from the execution of the program itself. And because the input bytecode in early Java or C# was so high-level, effectively just serialized ASTs under a different name, the JIT had to start from scratch every time.
Start from scratch doing what?
It had to do all the basic, mundane, totally obvious optimizations while the user was sitting there waiting.
Okay, what kind of mundane optimizations are we talking about here?
Things like dead code elimination or constant folding. Like if you wrote x equals 24 times 60 to calculate seconds in a day, a static compiler just turns that into 86,400 once at compile time.
Right, it just does the math.
But these early JITs were often having to figure that out on the fly. Or common sub-expression elimination, where it has to scan the code to realize you are calculating the exact same mathematical formula 3 times in a row, and it should probably just do it once and save the result.
Having a JIT do that work at runtime is a massive waste of resources.
Huge waste. Is trying to do the heavy lifting of a dedicated static compiler in a fraction of a millisecond, while also trying not to freeze the user's mouse cursor.
So the JIT can't do the really deep, aggressive interprocedural optimizations because it just physically doesn't have the time budget.
Exactly. It does the bare minimum to make the code run and then gets out of the way. It's a compromise that leaves an enormous amount of performance on the table.
Okay, which brings us to approach 3, compile time profile-driven optimization. This is the holy grail of performance that we joked about at the very beginning. The thing everybody claimed they were going to do, but nobody actually did.
Ah, yes.
Yeah.
The 5-stage bureaucracy. I absolutely love talking about this because it highlights the fundamental disconnect between academic theory and actual software engineering practice.
It is literally 5 stages of pure friction. Let's walk through it. Imagine you're a developer. You want to optimize your database engine based on how it actually runs in the real world. Step 1. You tell your compiler to build the program, but you pass a special flag that injects a bunch of instrumentation code into it.
Like adding sensors to a car.
Exactly. It sprinkles invisible counters, timers, and branch trackers throughout your code. Step 2. The linker takes those instrumented object files and binds them into a special, bloated, slow-running tracking executable.
And we are only on step 2.
Step 3. You, the developer, have to take this sluggish tracking executable and run it through a series of highly representative test runs. You have to simulate what you think the user is going to do to gather the profile data into a giant log file.
Which is tedious.
Very. Step 4. You take that massive log file, feed it backward into the compiler, and tell it, okay, now recompile the entire program from source, but use this log file to figure out which branches are hot and which loops are actually used.
Almost done.
Step 5. You relink the whole thing one more time to get your final optimized release executable.
Let's be brutally honest here. If you are a developer staring down a Friday afternoon deadline, you're absolutely skipping steps 1 through 4.
100%.
You are just shipping step 5 without the profile data. Nobody wants to maintain a 5-step, deeply fragile build process.
Especially
If you are building a graphical application, like how do you script a profile run for a video editor?
you can't.
You have to literally sit there and manually click menus and drag sliders to generate the profile data. It's absurd.
And even if you do have the ironclad discipline to actually do it, maybe you're building a command line tool. And it's easy to we circle right back to the lie from our cold open.
The poisoned data.
Exactly. The data you gather in step 3 is fundamentally poisoned. Your test runs in the lab, your automated Selenium scripts clicking buttons perfectly. They do not match the chaotic entropy of what the user does in the wild.
They never do.
You might end up meticulously optimizing the program for the exact opposite of what the end user actually needs. You spend an hour optimizing the CSV parser, and the user only ever uploads JSON files.
If we pull back and look at the bigger picture here, all of these traditional compilation models share a fundamental flaw.
Okay, hit me with an analogy.
They are like designing a massively complex spaceship here on Earth. You bolt everything down, you weld all the bulkheads shut, you lock in the aerodynamics, and you make all your calculations based strictly on Earth's gravity and atmospheric pressure. And then you launch it into deep space. Once it's up there, it's rigid. It is permanently fixed. It cannot adapt. If it encounters a bizarre nebula or a localized gravity well or cosmic radiation it wasn't expecting, it just has to push through using its original rigid design. It's completely inflexible.
And LLVM, how does Lattner's thesis attack this?
LLVM is proposing a shape-shifting ship. Lattner imagined a ship that continuously observes its own environment, continuously monitors how the crew actually flies it, and physically reorganizes its own bulkheads, engines, and life support systems based on the actual real-time conditions of deep space.
I mean, that is a wildly ambitious sci-fi analogy, but looking at the architecture of this thing, it actually holds up. Let's really get into the weeds of the shape-shifting ship. Let's tear down the LLVM architecture and its virtual instruction set.
You'll do it?
Because Lattner didn't just tweak the existing compilation process. He didn't just add a faster linker or a smarter JIT. He completely blew up the foundation and introduced a radically new 4-stage architecture.
He essentially looked at the compile, link, execute model and said, that's cute, but we're going to do compile time, link time, runtime, and idle time.
Okay, let's walk through the life cycle of a piece of code under LLVM. Stage 1, compile time. You write your C++ code, the static compiler front end, which today we know as Clang, but back then was a modified GCC, reads your code.
But instead of translating it down to dumb native machine code,
or leaving it as a giant, bloated, abstract syntax tree. Yeah,
Right.
It translates the code into the LLVM virtual instruction set. We are going to spend a lot of time on this instruction set in a minute, but the vital takeaway is that it's a Goldilocks representation.
Right. Not too high, not too low.
Which is right. Exactly. It is low level enough that it looks a lot like assembly language simple operations moving data around, but it stubbornly retains high level type information. It remembers what a struct is. It remembers what an array is.
So the static compiler can actually do useful work.
Yes. The front end does all the obvious basic file-level optimizations immediately. It folds the constants, it cleans up the obvious dead code, it does the heavy lifting, and it spits out these LLVM object files.
Which keeps things fast.
Extremely fast. It keeps the compile time incredibly fast for the developer. You change one file, only that one file is recompiled into LLVM bytecode. No sandwiches required. You don't lose your train of thought.
Then the developer types make,
Yeah.
and we enter stage 2, link time.
Right. The LLVM linker stepped in. It takes all these individual LLVM object files you just built, stitches them together, and because it is looking at that Goldilocks representation low-level operations, but with perfect high-level type information, it can perform aggressive interprocedural optimizations across the entire program.
It can see the big picture.
It can inline functions across file boundaries. It can safely delete entire blocks of memory structures if it proves no file if it uses them. It is doing the deep analysis that the AST folks tried to do, but it's doing it blazingly fast because the representation is so close to the metal.
And once it's done massaging this massive bytecode program, it finally generates the actual native machine code for your specific Intel or AMD processor.
But here is the plot twist. This is the moment in the thesis where you realize Lattner is playing a completely different game than everyone
Oh,
else.
this is my favorite part.
When the LLVM linker generates that native executable dash the actual .exe file on Windows or the ELF binary on Linux dash, it doesn't just write the native machine code and call it a day. It takes a heavily compressed copy of the entire program's LLVM bytecode and permanently embeds it directly inside a hidden section of the executable file.
That broke my brain the first time I realized how it worked.
Right. The executable carries its own source DNA around with it. It's like a compiled binary that somehow still remembers exactly how it was built and what all of its data structures actually mean.
It is brilliant. It is carrying the blueprints inside the house, which perfectly sets up stage 3, runtime.
Right. So you ship this executable to the user. The user double-clicks the app. It launches instantly because it's executing that lightning-fast, heavily optimized native machine code. It's not a slow JIT startup.
Right. There's no lag.
But quietly, hidden in the background, the LLVM runtime optimizer wakes up. It sits there, silently monitoring the execution. It's essentially doing that 5-stage profiling we talked about, but it's doing it completely transparently.
Gathering data on the fly.
It's gathering empirical profile information based on what the user actually does. It notices, oh, the user always takes the true branch of this specific if statement, or, wow, this database query function is being hammered way harder than the developer expected.
And if this were a normal Dynamo-style machine code optimizer, it wouldn't be able to do much with that information. It would just be staring at raw bytes.
Exactly.
But because the executable is secretly carrying that embedded LLVM bytecode blueprint, the runtime optimizer doesn't have to guess what the raw machine code means. If it sees a massive bottleneck, a hot path, it can refer back to the embedded bytecode.
It consults the blueprint.
Yes. It looks at the high-level control flow, the type information, and it says, I know exactly what this memory structure is. It can then do lightweight, highly targeted optimizations dynamically. It can literally rewrite the running native machine code in memory on the fly to make it faster for that specific user's exact workflow.
It is the shape-shifting ship in action.
It really is.
Which brings us to stage 4, and I know this is your absolute favorite concept in the entire paper.
Well, I am obsessed with stage 4. Stage 4 is idle time, the offline reoptimizer.
What happens when the user gets up from their desk to go make a coffee?
The machine goes idle. The operating system signals that the CPU has nothing to do. Now remember, during runtime, the LLVM optimizer has been quietly collecting all this beautiful, highly accurate, real-world profile data based on how the user actually behaves, not how the developer guessed they would behave.
Real data.
Real data. It saves that rich telemetry to the disk. So the moment the CPU goes idle, the offline reoptimizer wakes up in the background. It takes that golden profile data, it reaches into the executable to grab that embedded LLVM bytecode blueprint, and it goes to war.
It performs the massive, heavy, aggressive, profile-driven interprocedural optimizations that developers were too lazy to do in the lab.
Exactly. The kind of brutal, complex mathematical graph analysis that would normally freeze your computer for 10 minutes if a JIT tried to do it.
But it doesn't freeze the computer.
No, because it does it silently, in the background, while the screensaver is running. It completely recompiles the application using perfect real-world data, writes a brand new, hyper-optimized native executable to the disk, and goes back to sleep before the user even gets back with their coffee.
So the program literally evolves. It physically mutates on your hard drive while you are away from the keyboard, reorganizing its own internal architecture based entirely on how you treated it when you were using it.
It is the ultimate realization of continuous optimization. It completely solves the developer profiling lie we opened with. The developer doesn't have to do anything. The system gathers the profile in the field, and the software essentially recompiles itself.
Okay, conceptually, this sounds like absolute magic. It sounds like science fiction. But to understand how LLVM physically pulls this off without bringing the computer to a grinding halt, we have to look under the hood at that LLVM virtual instruction set.
We have to get into the bytecode.
Because you can't just do this with normal by86 assembly language. By86 is a nightmare. You need a very specific, very clever, mathematically pure representation of the code.
The representation is everything. If you get the representation wrong, the whole 4-stage architecture collapses.
Explain that.
Well, if the bytecode is too high level, like a Java AST, the static compiler at stage 1 can't do any meaningful optimization work, and the runtime JIT chokes to death trying to process it. If the bytecode is too low level, like raw machine code, the linker and runtime optimizer are flying blind.
So what did Lattner do?
Lattner's LLVM bytecode is a low-level, three-address code representation, but it enforces strict, uncompromising, high-level typing rules.
Let's break that jargon down for the listener. Three-address code is a fundamental compiler concept. It means almost every instruction in the language takes exactly one or two inputs, performs a single operation, and produces exactly one output.
Very simple, very linear.
Right. It is very simple, and it maps very closely to how physical silicon actually works. You say add X and Y and store the result in Z. That's three addresses. But the truly crazy part of LLVM's design isn't the instructions, it's the registers.
The infinite registers.
Yeah. A physical CPU, like our 2002 Pentium 4, has a strictly fixed, very small number of physical hardware registers. Maybe 16, maybe 32. It's a tiny workspace.
LLVM completely ignores physical reality.
It does. LLVM says, forget the hardware constraints. In this virtual instruction set, you have an infinite, boundless number of virtual registers.
Infinite registers are great, but they come with a catch, and it's a massive catch. They must follow a mathematical rule called static single assignment form, SSA.
SSA.
Okay, this is the beating heart of LLVM's speed.
Okay, yes. SSA. This is the concept that absolutely broke my brain when I first encountered it in compiler design.
Okay.
So, you're telling me in SSA form, every single variable, every single virtual register in my entire program can only be assigned a value exactly once.
Exactly once. It is immutable from the moment it is created.
Okay. My practical engineering brain is throwing massive red flags right now. If I'm writing a standard basic for loop in C++A and I have a counter variable like I equals I plus 1, I am mathematically updating that exact same variable I on every single iteration of the loop 1,000 times.
Right.
In LLVM's SSA form, you're telling me I cannot do that. I am literally forbidden from overwriting.
You are absolutely forbidden. In the LLVM representation, I does not exist as a mutable bucket of memory.
Then what happens?
You have %I1 for the first loop, %I2 for the second, %I3 for the third, and so on. Every single time a new value is computed, the compiler implicitly conjures a brand new, uniquely named virtual register into existence to hold it.
Why? That sounds insanely inefficient. You're taking a single integer and exploding it into thousands of separate variables? Aren't you just punting a massive memory mapping problem down the line to the linker?
It sounds inefficient to a human who is used to thinking about recycling memory buckets.
Yeah.
But to an optimization algorithm, SSA form is absolute paradise. Let me use an analogy.
Please do.
So normal code, where you overwrite variables, is like a chaotic whiteboard. You write a number, you erase it, you write a new number over it.
Okay, I follow.
If an auditor comes in and wants to know exactly how that final number was calculated, they have to forensically retrace your entire day. They have to trace backward through your complex control flow, up through the for loops, across the if branches, just to find the exact moment you last touched that whiteboard.
It requires massively complex, computationally expensive data flow analysis algorithms.
Exactly. Now, SSA form.
Okay, I see where you're going. So SSA is like an accounting ledger.
Exactly. In SSA form, you are strictly forbidden from erasing anything. You can only write on a brand new line. It uses way more paper, sure, but the auditor, or the LLVM optimizer, can look at line 400, see a uniquely named variable like %x14, and know with absolute mathematical certainty that there is exactly one place, and only one place, in the entire millions of lines of code where %x14 was created.
Because it's literally in the name.
The definition of the variable is permanently, uniquely baked into its name. Finding the origin of any piece of data is trivial. It's an instant lookup.
Okay, the ledger analogy makes sense for linear code, but how do you handle branching control flow? Let's say I have an if statement. If it's raining, x gets set to 5, else x gets set to 10.
Standard branching.
Right. When the program execution merges back together at the bottom of the statement and I want to print x, how does the compiler know which x to use if they have to be completely different variables? It can't be %xrain and %xsun at the same time.
This is where Lattner introduces the phi node.
The Greek letter.
The Greek letter phi. It is a special magical instruction in LLVM. At the exact point where the control flow merges, the basic block immediately following the if-else block, the compiler inserts a phi node.
What does it do?
The phi node basically acts as a data traffic cop. It says, I am conjuring a new variable, let's call it %xfinal. If the execution path just arrived here from the rain block, I will reach back and grab the value of %xrain. If the execution path arrived here from the sun block, I will reach back and grab the value of %xsun.
Oh, wow.
It cleanly and explicitly merges the bifurcated control flow based entirely on the provenance of where the program just came from.
It's a literal track switch for a train. It seamlessly routes the correct unique value forward onto the main track based entirely on which branch line the train just rolled in from.
Precisely. And because of this strict SSA property, because every value is born once, lives forever, and is explicitly routed through phi nodes optimizations that used to take order n squared time to calculate suddenly drop to order n or even order 1.
Just constant time lookups.
Yes. Algorithms like aggressive dead code elimination or common subexpression elimination just blaze through the code base. The algorithms don't have to guess or trace dependencies. The dependencies are explicitly physically wired together in a massive mathematical graph.
All right, so we have an infinite number of virtual registers. Every value is defined exactly once, and they're all connected by phi nodes. What else makes this instruction set special? Lattner notes that the instructions are polymorphic.
This is a massive space-saving feature, which is vital if you were trying to compress this bytecode to embed it into an executable.
Why does it save space?
Think about a traditional architecture, like by86 or a typical JVM bytecode. You have different opcodes for every conceivable variation of an operation. You have an add instruction for 32-bit signed integers, a completely different opcode for unsigned integers, another opcode for single precision floating point numbers, another for double precision.
It causes the instruction set to explode into hundreds or thousands of distinct commands.
Exactly. LLVM essentially says, that's stupid, we just have add.
Wait, if there's only one add instruction, how does the compiler know what hardware operation it's actually supposed to perform? Adding floats and adding integers require completely different silicon on the CPU.
Because the infinite virtual registers are strictly uncompromisingly typed. The add instruction itself doesn't need to know what it's doing. If you feed two floating point virtual registers into an add instruction, the instruction automatically inherits the context and acts as a floating point add.
The types dictate the action,
The strict type of the operands dictates the semantics of the operation.
which keeps the instruction set incredibly tiny, orthogonal, and simple. It's essentially stripping away the redundant grammar. And because the instruction set is so small, the bytecode is highly compressible, which is exactly why the linker can afford to embed it inside the native executable without blowing up the file size.
You're connecting the dots, yes. The architecture directly enables the multi-stage optimization strategy.
Okay, let's talk about memory. Because the memory model in LLVM is beautifully, brutally unified. If you look at a lot of high-level languages, memory is a complete mess of implicit and explicit behaviors.
Oh, it's a disaster.
Sometimes things are on the stack, sometimes they're on the heap, sometimes you're taking addresses, sometimes you're passing by reference. But in LLVM, there are absolutely no implicit memory accesses. If you want memory, you have to explicitly ask the LLVM runtime for it, and you get a strongly typed pointer back.
Right, and LLVM forces you to distinguish exactly where that memory is going to live and how long it's going to survive. If you want memory on the vast pool of dynamic memory that survives across function calls and has to be managed, you explicitly use the malloc instruction.
It carves out the space.
It carves out the space, returns a type pointer, and you eventually have to clean up your mess with the free instruction.
But what if you just need temporary memory? Say, a local variable inside a function that should just evaporate the moment the function finishes.
Then you use the alloca instruction. It allocates memory directly onto the execution stack. It also returns a typed pointer, but the beauty is that the memory is automatically instantly reclaimed the moment the function executes a re-instruction. It's extremely fast.
And what about global variables? Things that exist for the entire lifetime of the program.
LLVM's treatment of global variables is incredibly elegant. Global variables are just memory addresses. They're essentially static memory allocations that are initialized at load time.
Right.
But the deeper beauty here is that LLVM completely eliminates the concept of an addressive operator.
Wait, what do you mean?
In C++ Beria, if you have a variable x and you want its memory address, you prepend it with an ampersand.
Right, ampersand x.
LLVM doesn't do that. Addressable objects are always strictly accessed by their pointer address.
Why does that matter so much to the optimizer?
Because it simplifies the world. It means that absolutely all memory traffic, every single read and every single write to RAM, only ever happens through two very specific explicit instructions, load and store. If you are writing a complex compiler analysis algorithm trying to track memory usage or find memory leaks, you don't have to scan through thousands of bizarre instructions guessing if one of them secretly touches RAM. If an instruction is not explicitly a load or a store, it does not touch memory. Period.
That is a guarantee that makes analysis incredibly fast.
Exactly. It makes the graph so much easier to build.
Okay, one more critical feature of the instruction set before we move on, exception handling.
Ah, yes. The invoke instruction. This is where LLVM flexes on traditional language runtimes.
Big time. In languages like C++ or early Java, handling exceptions, when your code hits a massive error and throws a panic, can add a terrifying amount of overhead to your program.
Slows everything down.
The compiler has to inject all this hidden bookkeeping code just in case an exception happens. If an exception is thrown, the system has to violently unwind the execution stack, figure out which destructors need to be called to clean up memory, and desperately search up the call chain to find the right catch block. It is slow and bloated.
But LLVM uses what's called a zero-cost exception model.
Now, it's zero cost unless an exception is actually thrown, right? It's not magic.
Correct. When you write standard happy path code that doesn't throw exceptions, it runs exactly as fast as raw, unchecked C code. There's absolutely zero runtime overhead for preparing for an exception.
But how does LLVM actually track where to go if disaster strikes?
It completely removes the concept of language-specific try-catch blocks and replaces them with the fundamental invoke instruction.
So instead of a normal function call, you use invoke.
Yes. The invoke instruction takes the normal function arguments you'd expect, but it also explicitly takes two destination labels. A normal return label to go to if the function succeeds, and an exception handler label to jump to if the function violently fails.
So it is explicitly graphing the bifurcated control flow for the exceptional case right there in the instruction set.
Yes. When the static compiler front end generates the native machine code, it builds a massive, hidden, static lookup table behind the scenes. This table links the physical return address of the function directly to the exception handler label.
Oh, so it just maps it out ahead of time.
Right. If an exception is actually thrown at runtime, the LLVM unwinder pauses execution, looks up the current return address in that static map, and instantly knows the exact memory address to jump to handle the disaster.
That's incredibly clean.
It maps wildly complex, high-level C++ or Java exception semantics entirely using low-level language-agnostic concepts. It completely decouples the exception mechanics from whatever language the front end was compiling.
This is just brilliant engineering design. It's aggressively stripping away all the language-specific weirdness, the syntax sugar, and exposing the raw, fundamental mechanics of execution.
Which sets us up perfectly for my favorite part of the paper. Because Chris Lattner does not hold back.
Yeah.
This thesis is essentially a polite, rigorously cited takedown of a decade of bad compiler practices.
Oh, let's go. Time for some hot takes and hard truths. Because to truly appreciate LLVM, we need to look at the massive trade-offs it made, we need to roast the bloated approaches that failed, and we need to celebrate the genuinely clever hacks that made this work.
I am so ready for this.
I want to start with a roast.
Fire away. Let the hate flow.
I am roasting the bloated AST approaches, the abstract syntax trees of SU and SGI Open64 that we talked about earlier. We laughed at them for serializing gigabytes of text to disk, but you have to understand the sheer, unadulterated architectural bloat these things had. Open64 had a proprietary internal representation called Wordshell.
Oh, no.
Do you know how many distinct, separate levels of representation Wordshell possessed?
I do, but say it for the listener so they can feel the pain.
Five completely different levels of representation just to translate from C++ source code down to machine code.
That's ridiculous.
Very high whirl, mid whirl, low whirl, and very low whirl.
It sounds like a menu at a terrible coffee shop.
It's insane. The compiler had to constantly lower the tree, translating the entire program from one distinct dialect of WHRL to the next over and over again. That is not a compiler architecture. That is a sprawling, inefficient bureaucracy.
It's just moving paperwork around.
Exactly. Think about it from a modular engineering standpoint. You can't write a clean, universal optimization pass if you have to constantly check which of the 5 distinct levels of representation the code is currently sitting in. It completely destroys the ability to easily mix, match, and reorder compiler transformations.
So LLVM just bypasses that entirely.
LLVM looks at that mess and just says, absolutely not. 1 representation, strongly typed, 3 address SSA bytecode. We use it at compile time, we use it at link time, we use it at runtime. Deal with it.
It is the ultimate expression of engineering pragmatism over academic purity. Okay, my turn. I want to celebrate something. I want to celebrate the single greatest hack in the entire LLVM instruction set, the getElement PDR instruction.
Oh man, getElement PDR. This is the absolute magic bullet for maintaining type safety in a low-level language. Break down how this wizardry works.
Think about how you access a specific field inside a complex data structure in a low-level language like C. Let's say you have a struct representing a 3D point, and it contains three integers, x, y, and z.
Okay, standard struct.
If you write code to access the y variable under the hood, a normal C compiler does something terrifying. It treats the pointer to the struct not as an object, but as a raw, dumb memory address.
Just a location in RAM.
Right. It calculates that an integer takes up 4 bytes of RAM. So to find ham, it takes the base address of the struct, literally adds 4 bytes to that memory address to skip over x, and reads whatever raw bits happen to be sitting there.
It is raw blind byte math.
It's caveman stuff. Which means the moment that code is translated, the optimizer just sees an instruction that says add 4 to this hex address. It has completely and utterly lost the crucial context that you are explicitly trying to access the y field of a specific point struct.
And if you lose that high-level context, you cannot confidently optimize memory structures later.
Exactly. You can't safely rearrange the fields of the struct to be more cache efficient because you don't know if some random piece of code is relying on that exact byte offset.
So how does get-element PTR fix this?
Get-element-PTR brilliantly fixes this. Instead of doing raw byte math, the get-element-PTR instruction takes a strongly typed pointer to the struct and an index array. You literally instruct it, take this pointer to a point struct and get me the mathematical address of field number 1.
And it calculates the exact memory offset for you, but crucially, it retains all the structural type information.
Yes. The optimization algorithm scanning the code sees the get-element-PTR instruction and says, I understand. You are safely, explicitly accessing the allowable field of a point object.
It perfectly bridges the gap between low-level pointer arithmetic and high-level object-oriented type safety. It's the linchpin that allows LLVM to be a lightning-fast, low-level representation while still acting like a rich, high-level AST.
It is deeply elegant. But, and this is big, but this celebration leads directly into my hard truth. The most provocative, cynical take in the entire thesis.
I love cynical takes. Hit me.
Type-safe C code is a total myth.
That broke my brain when Lattner pointed it out. C and C++ are statically typed languages. That's the whole point. We meticulously define our ints, our floats, our complex nested structs.
We define them, yes. And then we completely brazenly ignore them whenever it's convenient.
What do you mean?
We take raw integers and violently cast them into memory pointers to access hidden hardware registers. We take a pointer to a meticulously defined network packet struct and cast it into a generic character pointer just so we can blindly read the raw bits off the wire. C actively encourages you to do absolutely unhinged, dangerous things with memory. It is an intrinsically, fundamentally unsafe language.
Okay, wait. If LLVM completely relies on strict type information to do its magical whole program optimizations, how does it handle billions of lines of legacy C code that constantly violate the rules of type safety?
That's the billion-dollar question.
Doesn't the whole elegant mathematical graph just come crashing down the moment someone uses a raw pointer cast?
This is where Lattner's design is just ruthlessly, brilliantly practical. LLVM introduces the cast instruction. In LLVM bytecode, you cannot implicitly convert data types. You can't just casually treat an integer like a float. The compiler refuses. You have to explicitly, intentionally use the cast instruction to force the conversion.
Okay, sure, explicit casting, standard stuff.
But here's the genius part. The LLVM compiler architecture explicitly categorizes certain cast operations as inherently unsafe.
Unsafe, like which ones?
Specifically, if you cast a non-pointer like an integer into a pointer, or you cast a pointer of one struct type into a pointer of a completely different incompatible struct type.
Which people do all the time in C.
All the time. When that happens, LLVM quietly flags that specific cast instruction as unsafe.
So it doesn't stop you from compiling bad C code. It doesn't throw a syntax error.
No. It explicitly allows the bad, dirty C code to compile. It doesn't try to prevent developers from writing bad code. It just makes absolutely sure to explicitly track it.
Oh, that's smart.
When the optimization algorithms are running their massive graphs, they sweep through the code. If they see an unsafe cast instruction flag, the optimizer basically throws its hands up in the air and says, whoa, okay. The programmer's doing some sketchy, undocumented black magic here.
So it backs off.
Yeah, it says, I will not make any assumptions about what happens to this specific block of memory. I will degrade gracefully.
That is a phenomenal engineering hard truth. You don't try to force millions of stubborn developers to write perfect, mathematically pure code. You just build a system that meticulously tracks the imperfect code so the optimizer knows exactly where the landmines are buried.
Exactly.
If a section of code is perfectly type-safe, the optimizer goes wild and makes it blindingly fast. If it hits an unsafe cast, it plays it defensively safe.
It isolates the chaos.
Yeah.
And it works. It really, really works.
Time for a metrics check to prove that it actually works outside of an academic vacuum. Let's look at the Spec INT 2000 benchmark stats that Lattner published in the paper. Because theorizing about elegant graphs is one thing, but running it on massive, bloated legacy code bases is the real test.
Let's hear the raw numbers.
They ran the LLVM infrastructure on a notorious benchmark called 254.gap. This is not some tiny toy program written for a thesis. This is 71,000 lines of incredibly dense C code.
A total beast of a program.
It's an interpreter for a computational discrete algebra system. When compiled into LLVM bytecode before any optimization, it produced 345,000 distinct LLVM instructions.
It's massive.
Massive. They unleashed the aggressive dead code elimination pass on it, ADCE. This is an incredibly complex global analysis pass. It sweeps the entire program looking for complex webs of code that compute mathematical values that are never ever actually used or printed by the program, and it deletes them.
And how long did it take? Remember, SGI Open64 would take minutes to do this.
Yeah. It processed the entire 71,000 lines of code, traversing all 345,000 instructions. It took 1.42 seconds.
Wow. 1.4 seconds.
1.42 seconds. That mathematically breaks down to 4.12 microseconds per instruction. That is blindingly, shockingly fast. And in that second and a half, it successfully identified and deleted almost 4,000 dead instructions that the standard GCC compiler completely failed to find.
Which is an absolute triumph of the SSA form we talked about earlier.
Because it's a graph.
Because the definitions and the uses of every single variable are directly, explicitly wired together with unique names. The ADCE algorithm doesn't have to do complex guessing. It just drops onto the graph, walks the explicit pathways, finds the variables that have zero dependent branches, and snips out entire dead branches of logic instantly.
Right. It completely empirically validates Lattner's crazy decision to use infinite virtual registers in SSA. It makes these macroscopic passes incredibly lightweight.
Okay, let's bring this down from the clouds and make it tangible for the listener. We've talked a lot about theory, graphs, and metrics. Let's walk through some practical line-by-line demos.
Let's do it. Let's really paint a picture of what these compiler passes actually do to the code to make it faster.
I'll ask the questions, you walk us through.
Sounds good. Let's do two specific demos. First up, the level raise pass.
Ah, yes, the great undoer of bad C front ends.
Exactly. Imagine you are writing a simple piece of C code. You define a struct, let's call it S1. It's very simple. It just contains two standard integers. Let's call them I and J.
Simple enough.
Then you write a tiny one-line function. It takes a pointer to an S1 struct, and it returns a simple calculation. S arrow I times 4 plus S arrow J. You are just doing some basic math on the two fields.
Nothing crazy. What does a naive traditional C compiler front end do with this beautiful, simple code?
It panics and emits the most poorly typed, ugly, raw pointer math you can possibly imagine. To get the I field, it takes your beautiful struct pointer, aggressively casts it down to a raw, dumb integer pointer, and issues a load command.
Okay, fine. That gets you the first integer.
Then it multiplies it by 4. But to get the J field, it takes the base memory address, casts it to a raw 64-bit long numeric type, literally adds 4 bytes to the numeric address to skip past the first integer.
Because an int is 4 bytes.
Right. Then it violently casts that resulting raw number back into an integer pointer and issues another load command.
It's disgusting. It has completely lost the abstract concept of the S1 struct. It's just a caveman doing raw memory arithmetic with a club.
Right. And if you feed that caveman output into a sophisticated interprocedural linker, the optimizer is totally blind. It doesn't know you are touching the S1 struct. It just sees random byte addresses being tweaked.
So LLVM introduces a magical pass called level raise. What does the level raise pass actually do when it scans this mess?
It acts like a digital code archaeologist. It sweeps over the bytecode. It looks at the function prototype and sees, okay, the developer explicitly declared that this function takes an S1 struct pointer. It then looks down at the gross byte math instructions the front end generated.
And it spots the weird math.
It sees that suspicious addition of exactly 4 bytes to the base address. It cross-references the global definition of S1 and has an epiphany. It realizes, wait a minute, a standard integer is exactly 4 bytes long. Adding 4 bytes to the base address is mathematically identical to accessing the second field of the struct.
So it actually rewrites the bad instructions.
Yes, it literally deletes the ugly, unsafe cast instructions and the dumb addition instruction. It rips them out and replaces them with a beautifully safe, perfectly typed get telement PDR instruction that explicitly says, get field number 1 of the S1 struct.
That is just gorgeous.
It literally raises the semantic level of the code from raw, dangerous machine-level bytes back up to high-level, mathematically safe structure accesses.
It forensically recovers the type information that the bad C front end carelessly threw away. That is the power of the architecture right there.
Okay, that's a microscopic optimization. Demo 2. Let's go macroscopic. Let's talk about the absolute deep magic, automatic pool allocation.
Oh, this is the one that proves LLVM is operating on a different plane of existence.
Imagine you're writing a massive hospital management system. You have a function called process lists. It grinds through data and creates 2 entirely separate, massively long, disjoint linked lists of patient data. Maybe one linked list is for processing thousands of new admissions, and the other linked list is for processing thousands of discharges.
In a normal standard C or C++ program, how do you build linked list? You write a loop, and for every single new patient node you need to create, you call the system malloc function to ask the OS for memory.
Right, and what actually happens to your physical RAM when you call malloc 10,000 times in a row for tiny objects?
Your heap memory becomes an absolute, deeply fragmented nightmare.
Explain the nightmare.
The malloc function is basically a frantic real estate agent. It just grabs whatever tiny scrap of free memory it can find anywhere on the RAM chip. So your logically connected linked list nodes are physically sprinkled randomly all over the gigabytes of physical RAM.
So they aren't next to each other?
Not at all. Node 1 is at memory address 1000, node 2 is at memory address 8000, node 3 is at address 2500.
And why is that bad?
Because of the CPU cache. When you try to traverse that linked list later to calculate a report, the CPU tries to prefetch the memory. But because the nodes are scattered randomly, the CPU cache completely fails.
It guesses wrong.
It suffers massive page faults. It has to constantly halt execution, wait hundreds of clock cycles for the main RAM to fetch a completely different physical sector of memory, process one node, and then halt again. It absolutely destroys runtime performance.
Right. It's like trying to read a book where every single page is located in a different library across the city.
Perfect analogy. So, enter LLVM's data structure analysis and automatic pool allocation pass. How does Lattner solve the real estate problem?
At link time, LLVM runs a data structure analysis over the process lists function. It aggressively traces the flow of pointers, it tracks every single malloc call, and it builds a literal, field-sensitive mathematical graph of how the memory is logically connected.
And it realizes, I see what the human is doing. This code is creating 2 completely separate, parallel linked lists.
And crucially, it mathematically proves that those 2 lists never physically intersect, and that the developer is using them in a perfectly type-safe way without weird pointer casting.
Yes. The moment it proves that, the automatic pool allocation pass takes over and completely rewrites your software architecture. It permanently deletes your calls to the global OS malloc.
Rooks them out.
Rooks them out. Instead, at the very beginning of the function, before the loops even start, it allocates 2 massive, perfectly contiguous pools of memory. One giant pool specifically reserved for the admissions list, and one giant pool reserved for the discharges list.
And then it actually rewrites the memory allocation calls inside the loop.
Exactly. It changes the malloc calls to internal pooloc calls, passing in a hard-coded reference to the specific pool. So now, when the loop runs, all 5,000 nodes for the admissions list are allocated right next to each other sequentially in memory pool A.
And all the discharges are in pool B.
Packed tightly together in memory pool B.
So later, when your reporting function traverses the list, the memory is perfectly physically organized. The CPU cache just streams the contiguous data in from RAM at maximum hardware speed.
The performance leaps exponentially without the developer changing a single line of their terrible C code. I love the analogy they use for this from the olden benchmark suite.
Oh, the power benchmark.
Yeah. They ran this automated pass on a famous benchmark called Power, which generates a massively complex tree data structure. It has a central root node, which points out to lateral nodes, which point to branch nodes, which point to thousands of leaf nodes.
Right.
When you use standard malloc, it scatters these nodes everywhere. It looks like a messy, chaotic galaxy of stars scattered randomly across the void.
And when the pool allocator steps in,
the pool allocator runs its data structure analysis, perfectly understands the topology of the tree, and forcefully creates 4 distinct contiguous memory pools. One specifically for roots, one for laterals, one for branches, and one for leaves.
Wow.
It's like taking that chaotic, messy galaxy of stars and magically instantly organize them in neatly by planet class. All the gas giants are over here in this sector. All the rocky planets are over here.
And the CPU cache just eats it up.
The performance improvement is absolutely staggering because the physical memory locality perfectly matches the logical access pattern. And again, it happens completely automatic at link time without human intervention.
It's just phenomenal engineering, but, and I say this because I'm a pragmatic engineer, I don't believe in silver bullets. We need a reality check.
Yes, let's burst the bubble.
Because nothing in computer science is perfect, and if you read the back half of the thesis, Lattner's very honest about the limitations. Where are the boundaries of the magic? Where does LLVM hit a wall? Let's have you play devil's advocate for a minute.
Oh, gladly. I love finding the breaking points. Let's talk about where this beautiful, elegant, shape-shifting system hits a brick wall of reality. Let's start with that data structure analysis graph we were just praising, the one that neatly organized the galaxy of memory.
Right.
What happens to that fragile mathematical graph when a developer introduces pure, unadulterated chaos?
Pure chaos being.
Say I'm writing a low-level hardware driver. I literally take an arbitrary integer, say the literal hex number 0x deadbeef. I violently cast it into a struct pointer, and I start blindly writing data to it because I read in a manual that that's where a specific hardware graphics register lives.
Okay, yes. You are violating every single rule of type safety, memory safety, and common sense.
Right. So what does the data structure analysis algorithm do when it encounters that horrifying instruction? Remember, it's trying to build a neat, field-sensitive graph of memory.
Field-sensitive meaning.
Field-sensitive just means the compiler isn't seeing a generic blob of data. It sees the blueprint. It knows this specific byte is the patient's name, and this exact byte is their blood type, and it draws precise mathematical lines connecting them.
Okay, I follow.
But now I've just injected a rogue, untyped, completely unpredictable pointer directly into the middle of that delicate graph.
The graph completely collapses.
Exactly. The algorithm panics. It is forced to instantly drop its field sensitivity for that entire section of memory. It takes the elegant node representing that memory structure, and it literally collapses it down into a single, opaque, undifferentiated blob.
It just gives up on the details.
And crucially, it sets a specific warning flag on that node called the unknown bit, the U bit.
So the compiler essentially says, I don't know what the fields are anymore. Some human threw a chaotic pointer into the mix, so I must defensively assume that any write to this blob could overwrite any field at any time.
Yes, it retains conservative correctness, which is the golden rule of compilers. It means it absolutely will not optimize something illegally and accidentally break your program.
But
in exchange for safety, you lose all the optimization magic. If a memory node is collapsed and flagged with a U-bit, the brilliant automatic pool allocator we just talked about looks at it and refuses to touch it. It says, nope, too dangerous, I'm backing off. You get standard malloc.
So the magic is fundamentally brittle when faced with unsafe code. It doesn't break your program, but it punishes you with slow performance.
It degrades gracefully, but yes, you completely lose the macroscopic benefits.
Okay, here's another reality check. Hardware limitations. Specifically, CPU cache capacity misses on giant code bases.
The scaling problem.
Right. We talked earlier about how incredibly fast that 254.gap benchmark compiled 1.4 seconds. But if you actually dig into the data tables in the paper, a different story emerges about scaling.
They hit a wall.
They ran a much smaller benchmark, 300.wolf, which is only about 20,000 lines of code. It optimized in fractions of a second. But when they scaled up to 254.gap with 71,000 lines, or another one called 255.vortex with 67,000 lines, the compilation time didn't scale linearly. It scaled significantly worse. The graph curves up.
Why the slowdown? The algorithms are mathematically order n. They should scale perfectly.
Because of the physical reality of processor caches in 2002. Think about the sheer volume of data structures required to hold this perfect SSA form in memory. The infinite virtual registers, the thousands of phi nodes, the massive cross-referenced control flow graphs.
That's a lot of metadata.
For 20,000 lines of code, all of that data fit perfectly inside the Pentium 4's tiny internal L2 cache. The CPU never had to wait for RAM, it flew. But when you hit 70,000 lines of code,
it spills over.
Those internal graph data structures get massive. They physically spilled out of the CPU's blazing fast internal cache and spilled over into the slow external main system RAM.
Massive capacity misses.
Exactly. Every time the optimization algorithm needs to trace a pointer or check a phi node, the CPU cache misses, and the processor has to halt for hundreds of clock cycles to fetch the data from the slow main RAM.
So the algorithms themselves are theoretically incredibly fast, but the physical hardware bottlenecks the compilation process.
Right. When you are trying to do whole program interprocedural analysis on a million-line enterprise code base, the sheer volume of metadata you have to hold in memory simultaneously becomes a massive, crippling hardware problem.
And here's one more massive reality check that developers deal with every day. Incomplete programs.
Oh, this is a big one.
Lattner's whole program optimization is beautiful, but what if you don't actually have the whole program? What if you are compiling a video game, but it relies heavily on calling functions from a closed-source, pre-compiled graphics library, like DirectX or OpenGL, where you absolutely do not have the source code or the LLVM bytecode?
Oh, right. If you only have the compiled binary of the library, the LLVM linker can't see inside it.
Exactly. The interprocedural optimizer arrives at the boundary of your code, looks at the external function call, and is basically staring into a pitch-black box.
It has no idea what happens in there.
If your program passes a carefully constructed pointer to a struct into that black box function, the LLVM optimizer has to assume the absolute worst-case scenario. It has to assume that the external function might maliciously alter every single field of that struct, or secretly save the pointer to a global variable to mess with it later, or even free the memory entirely.
How does the data structure analysis graph handle a black box? Does it collapse the node again, like the U-bit?
It uses a different flag, the incomplete flag or the I bit. Any memory node in your beautiful graph that gets passed as an argument into an unanalyzable external function instantly gets flagged as incomplete.
And what's the consequence?
Just like the unknown bit, if a node is incomplete, all the aggressive macroscopic optimizations like pool allocation immediately back off. It forces the optimizer to stop making dangerous high-performance assumptions about memory that might be manipulated in the shadows.
So the truth is, the whole program optimization really only sings if you actually have the entire program.
Yep. If your architecture relies heavily on opaque external libraries, dynamically loaded plugins, or closed-source frameworks, the interprocedural magic gets significantly blunted.
It's the messy reality of the software ecosystem. But even with those severe limitations, the rogue pointers, the cache misses, the opaque libraries, what Chris Lattner built in this thesis is just foundational to modern computing. It completely shifted the paradigm of how we think about translating logic into silicon.
I really did.
Which means it's time to synthesize all of this down. We've gone deep into the weeds of 2002 compiler theory. Let's give the listener the actionable takeaways. If you are a developer building software architectures today, or designing languages, or just trying to write performant code, what are the core enduring lessons you can extract from Lattner's work?
I think the most vital lesson is about representation. High-level context and low-level packages.
But let's unpack that.
For decades, compiler engineers genuinely believed they had to make a binary choice. We thought we could either have a rich, complex, high-level representation with perfect type information, like a giant AST, which was incredibly slow and bloated to process.
The SGI Open64 nightmare.
Right. Or we could have a compact, blindingly fast, low-level representation like raw machine code, which was blind, dumb, and impossible to deeply optimize. LLVM empirically proved that this is a false dichotomy.
Right. By creating a low-level 3-address instruction set that stubbornly retains strict typing rules, LLVM proved you can have the absolute best of both worlds.
You can have a representation that is small enough and fast enough to literally embed inside a shipping executable file,
but rich enough to allow a runtime optimizer to safely perform massive whole program memory restructuring. You do not have to choose between execution speed and semantic context.
The second major takeaway fundamentally changes how we view the software lifecycle: continuous optimization. We have to stop thinking of compilation as a singular one-time event that happens on a developer's laptop.
The archaic compile link execute model is dead, or at least it absolutely should be.
It's obsolete.
The arrogant idea that a developer can perfectly predict and optimize a program in a sterile vacuum before the chaotic user ever touches it is a complete failure of imagination.
It is the rigid spaceship launching into the void. Real-world performance requires continuously observing software in the wild. You need to build architectures that can profile themselves dynamically, seamlessly adapt to edge cases, and literally re-optimize their own internal structure during idle time based strictly on actual human behavior.
The operational environment matters just as much as the source code.
Absolutely.
Okay, my favorite takeaway is about language design. Explicit is radically greater than implicit.
Oh, this is a huge one. In LLVM bytecode, absolutely nothing is hidden behind syntactic sugar. Memory allocations aren't magical background operations that just happen. They are explicit, undeniable allocate and malloc instructions.
You can't just wave your hands.
No. You don't just implicitly, quietly convert an integer to a float. You are forced to explicitly write a cast instruction. You don't have implicit address-taking operators that confuse the memory graph. Variables fundamentally are addresses.
By forcing all of these complex operations to be explicit, primitive instructions in the bytecode, LLVM makes tooling, debugging, and analysis exponentially easier. If an operation isn't explicitly stated in the instruction list, it mathematically does not happen.
It completely removes the guesswork for the optimization algorithms.
Which is exactly what makes the LLVM compiler both unbelievably fast and incredibly reliable.
And finally, the last takeaway, which goes back to our reality check. Embrace the unknowns.
Yes. Don't build fragile systems that shatter into a million pieces the moment they are faced with bad data.
Exactly. LLVM doesn't throw a temper tantrum and refuse to compile bad, non-type-safe legacy C code. It compiles the code, but it explicitly flags the unsafe casts.
It isolates the damage.
When the data structure analysis graph gets hit by a chaotic, untyped rogue pointer, the compiler doesn't crash. It just collapses the specific node, sets the unknown bit, isolates the damage, and degrades gracefully.
You have to build robust, pragmatic systems. Build an architecture that can isolate the chaos. Let the bad, dirty code run unoptimized, but do not let that one bad function stop the rest of your perfectly written, type-safe codebase from getting the aggressive, interprocedural optimization it deserves.
It is a profound philosophy of engineering resilience. Protect the core system, explicitly flag the danger zones, and keep moving forward.
It really is. Chris Lattner essentially looked at the bloated, agonizing mess of modern software engineering in 2002 and said, I can fix this, but I have to completely tear out the foundation of the house to do it.
And he actually did it.
And the fact that LLVM went on to become the underlying bedrock of Apple's entire ecosystem, the Swift language, the Rust compiler, and basically the entire landscape of modern high-performance compilation as we know it. It all started with the sheer audacity of this master's thesis.
You know, it really makes you wonder, doesn't it? If a compiler infrastructure designed over 2 decades ago can use a few minutes of CPU idle time to automatically, silently rewrite and optimize its own bytecode based entirely on how a human behaves.
Yeah.
How far are we, really, from software that doesn't just optimize its low-level instructions, but completely reinvents its own high-level architecture while we sleep?
Oh, wow.
Think about it. If an application realizes the user is interacting with it in a fundamentally bizarre, unexpected way, could a future infrastructure literally rewrite the core data structures, swap out the sorting algorithms, redesign the database schema in memory, and present a completely different, highly adapted application by morning?
It's entirely possible.
We are already seeing the foundational seeds of self-modifying, self-adapting, shape-shifting software right here in a paper from 2002. It's just a matter of scaling the concept.
That is a simultaneously terrifying and absolutely beautiful thought to end on. Software that literally dreams of a better, faster version of itself while you step away to make a coffee. I absolutely love it.
It is the shape-shifting ship finally off the ground.
All right, that brings us to the end. This has been another episode of our tech podcast, based on cited resources, LLVM, an infrastructure for multi-stage optimization by Chris Arthur Lattner. Find your weirdest edge case and share it. We love this stuff. Tell us what to cover next. Please leave a comment, subscribe if you like. Thanks for listening.